So, what if the empty space all around us isn't actually empty at all? We are about to dive into a truly radical theory that challenges, really challenges, our most basic ideas about the universe, from black holes to reality itself. This is the high stakes, high reward world of theoretical physics, where just one new idea could literally change everything.
And why do we even need new ideas? We'll take a look at this. This is our map of everything that exists. And that tiny little 5% slice, that's everything we know. Stars, galaxies, planets, you, me, this microphone. The other 95%, it's a complete and total mystery. Scientists have a name for it. They call it the dark sector. But honestly, that's just a fancy way of putting a giant question mark right at the heart of physics.
In fact, to be blunt, you could say physics is in a bit of a crisis. For decades, it's kind of been stuck, running into three huge, deeply embarrassing problems that our best and most trusted theories just can't solve. And we're not talking about small details here. These are fundamental contradictions about how the universe works.
Okay, first up, that dark sector. For a long time, the main theory was that it's made of some kind of undiscovered particles, nicknamed WIMPs. The problem? After decades of searching, using these massive, unbelievably sensitive detectors, we found, well, absolutely nothing. Zip. Nada. The ghost we've been hunting for all this time just doesn't seem to be there.
Second, we've got a cosmic puzzle called the Hubble tension. Put simply, when we measure how fast the universe was expanding way back in its infancy, and then compare that to how fast it's expanding today, the numbers don't line up. It's like measuring a child's height in the morning and then again in the evening and getting two totally different answers. It suggests our whole rulebook for measuring the cosmos is just broken. And third, the singularity. According to Einstein's masterpiece, general relativity, at the heart of every single black hole is a point of infinite density. But here's the thing. In physics, infinity is basically a code word for our math just broke. It's a flashing red light telling us that our best theory of gravity completely fails in the most extreme places in the universe. So with physics kind of stuck at a crossroads, what if the answer isn't some new particle we have to find? What if the problem is that we've misunderstood space itself? There's a radical new idea on the table that proposes the nothingness of the vacuum is actually the most important something in the entire cosmos. It's called dynamic vacuum field theory, or DVFT for short. Now, the core idea is simple, but it's totally revolutionary. It asks you to stop thinking of space as an empty box that things just move through. Instead, imagine space itself is a real physical substance, kind of like a tense muscle. It can store energy, it can vibrate, and believe it or not, it can flow. Here's a really great way to get your head around this. Picture two giants playing tug of war, and they're both pulling with literally infinite force. The little flag in the middle of the rope? It's perfectly still, right? Zero motion. But is there zero energy in that rope? No way. The rope is absolutely humming with immense tension. DVFT says that's what the vacuum of space is, a state of perfect, balanced tension, holding a massive amount of potential energy. And this is the real power of a big unifying idea. If you can accept that one single premise, that space is a substance, then suddenly those three cosmic crises we talked about, they start to look solvable. Let's see how this one idea just cleans house. So, how does it do it? Well, the dark sector? It's not missing particles, it's just the built-in energy and stiffness of the vacuum itself. The Hubble tension? That goes away because the vacuum isn't just a static thing. Its properties can actually change over billions of years. And those pesky black hole singularities? They're gone, replaced by a physical speed limit, the maximum density the vacuum substance can even handle. It's a beautiful example of Occam's razor, one simple idea that elegantly explains a whole host of problems. But the ambition here goes way further. You see, the ultimate holy grail of physics is to unite gravity with quantum mechanics. The standard approach, trying to quantize geometry, has been a mathematical nightmare for decades. DVFT just flips the whole problem on its head. It tries to get quantum behavior to emerge from the fluid-like properties of the vacuum. Think about how Boltzmann explained heat. It wasn't some magical fluid, it was just the jiggling of atoms. DVFT suggests gravity isn't some weird abstract geometry, it's the physical flow of this vacuum substance. Okay, but hold on. Any new theory, especially when this out there, has to run a brutal gauntlet of scientific challenges. I mean, these are the killer arguments that have shot down 99% of all alternative gravity theories in the past. To even be taken seriously, DVFT needs to have some rock-solid answers.
And the first attack is the biggest one. It's the ghost of physics past. Isn't this just the old, discredited ether theory? See, over 100 years ago, experiments proved that there's no cosmic wind that we're flying through. So any theory that says space is a substance, well, it seems dead on arrival.
But the theory has a really sophisticated defense. It's mathematically designed to be Lorentz invariant. Now, that's a technical term, but what it means is that the laws of physics look exactly the same for everybody, no matter how fast you're moving. It pulls this off by having the vacuum's properties change in a special kind of time, not our regular everyday time. The end result? Unlike the old ether, this substance creates no wind you can detect. You literally can't feel yourself moving through it.
All right, on to the next major challenge. This one is all about gravity's effect on light. Einstein's theory is famous for perfectly predicting how much a huge object, like our sun, will bend the path of starlight. But simpler theories, called scalar theories, always get this wrong. They only ever predict half the correct amount.
So how does DVFT solve this? Well, it actually agrees that the density change in the vacuum around a star only gives you half the answer. But then it adds a second, crucial effect, a kind of drag on light caused by the vacuum flowing into that massive object. And that flow, it provides the exact missing half, allowing the theory to perfectly match the observations and the predictions of general relativity.
So after all that, where does this leave us? We have a really high-risk, high-reward idea here. On one hand, it challenges the very foundations of physics. But on the other, it offers these incredibly elegant solutions to some of our deepest mysteries. So what's the verdict?
Now, it's really important to get this straight. While this is definitely an unorthodox idea, it is not a crackpot theory. It has a formal classification in physics. It's called a semi-classical hydrodynamic gravity theory. It's part of a serious, though small, field of research that looks at gravity as an emergent phenomenon.
The potential outcomes here are just staggering to think about. If it turns out to be wrong, it's still a really elegant toy model that could teach us new things about how gravity works. If it's partially right, it could completely replace our messy, complicated models for dark matter and dark energy. And if it's fully right, then we're looking at the successor to Einstein's general relativity.
And maybe that's the best way to think about this. The goal here isn't to say Einstein was wrong. The man was a genius. He perfectly described the geometry of gravity, the shape of it. This new theory just wants to go one level deeper to describe the physical substance whose behavior creates that shape in the first place. Which leaves us with one heck of a question. Are we finally ready to understand not just how the universe works, but what it's truly made of?